Alright guys, here's part 3. This time we are going to take the derivative of exponentials and logs with bases other than e. So, for example, we're going to look at things like y equal 5 to the 3x or y equal log base 5 of 3x. Now, these are not used that often. This one, this number to a function power, that one's used more often than this one, but we have to be ready for everything. So we're going to take a look at this one first. And this form is y equals a to a function power. So a is a constant, and u is a function. And u has to be a function that we know how to take the derivative of. And so we have no idea of what this particular rule happens to be. So I'm going to show you a technique that's sort of a catch-all. It's called logarithmic differentiation, and part 4 is going to be focused solely on that. But we're going to use it right now as a tool to try and get a rule for this. So what we're going to do is we're going to take the ln of both sides of this. So this is ln y equals the ln of our a to the u. And if you remember, this ln of a to the u, this power can drop in front of that logarithm as the use of one of our log properties. So I'm going to rewrite it like that before I take the derivative. So we get u times ln a. This we can take the derivative of. We're looking for dy dx. Remember, we're always looking for dy dx in these examples. And so we're looking for this derivative, and if I take the derivative of this implicitly, I can easily figure out what dy dx is. So I'm going to use my derivative rule for the ln of a quantity. So that's 1 over that quantity times the derivative of that quantity. And the derivative of y with respect to x is dy dx. Over here, the ln of a, this piece right here, the ln of a, is a number. It's a constant, like a 4. So technically, I can just pull him out front, because it's a number, and I can multiply by the derivative of u with respect to x, which is du dx. And now if I multiply by y, I get dy dx is equal to y times ln a times du dx. And if you remember, if I go back up here, this y was the original equation. So I'm going to get dy dx is equal to a to the u times ln a times du dx. So that's our new rule. Our new rule is, let me get a new slide here. If y equals any number raised to any function. So remember, this is a constant, like a 4 or a 2 or a 3, and this is f at x. Then our derivative, dy dx, is equal to whatever the original function was, exactly the way it appeared, times the ln of a times the derivative of the power. Right? So that goes on a note card. I want you to pause the video and write your note card based off of that. Alright, so now your note card's written, have it out, and let's take a look at some examples. So we want to find dy dx. And I'm only going to do 2 of these because once you get the hang of it, it's easy. It's just applying the rules. So the first example, y equals 5 to the 3x plus 7. So this is a to the u. What I don't want you to do is use the ln of both sides of this. I want you to remember this rule. The rule that you wrote on your note card, you have to remember it. You can't rely on taking the ln of both sides each time. And so what we're going to get here, the derivative, this is exactly the rule. There's no other rules in place. This is a to the u. So the rule is a to the u. So you take the whole thing and you rewrite it exactly the way it was written, times the ln of your base. So that's 5. And then times the derivative of the power. And the derivative of 3x plus 7 is 3. Done. The derivative of 5 to the 3x plus 7 is 5 to the 3x plus 7 times ln 5 times 3. All right, let's do another one. Y equals x squared times 3 to the 5x. All right, so now when you look at that, that's a product. So you're going to have to start that with the product rule. So the derivative is going to be x squared times the derivative of this piece. So this piece is a to the u. So we've got to use the rule on that. So it's 3 to the 5x, the whole thing, times the ln of the base, times the derivative of the power. And then plus the second piece, 3 to the 5x, times the derivative of the first piece, which is just 2x. I could get that to write better. Okay. So now I'm going to do the same thing we always did. I'm going to look for things to factor out. There's a 3 to the 5x in common, and there's x to a power in common. So we can factor it a little bit. We can pull out an x, and we can pull out a 3 to the 5x. And we're left with x times ln 3 times 5 out of the first part, plus this x is out, the 3 to the 5x is out, and we are left with only a 2 there. There you go. Final answer on that one, factored form, is x 3 to the 5x times that quantity there. All right? All right, so now let's keep going with a log of a different base. So if y equals log base anything, so base b of any quantity u. All right? I want you to remember from GT10 and from college algebra your change of base formula. So basically this is not a new rule. It's the application of an old thing, the change of base formula. And once you change this base, we're going to change it into an ln. So we're going to change base b into an ln. So if you remember, the change of base formula says if y equals log base anything of a quantity. See, my dogs are all excited about this new rule. They're barking and they're so happy about it. So this is going to be the ln of that quantity over the ln of b. And then once you get it into that form, this ln of b is just a number. So you can write it like this, 1 over ln b, because it's a constant, times the ln of u. And then you can easily differentiate that. So I want this piece on a note card. To find the derivative of log base b of u, use the change of base formula, put it into ln u over ln b, and then rewrite into that form. All right? So pause it, put that on the note card, and on the next slide we'll do an example. So example 1 here, if we're finding dy dx, we're going to do y equals log base 5 of 3x. So we don't have a rule for that. I mean, there is a rule, like in the books, there is a rule, but I think it's not worth remembering the rule. It's worth using what you already know sometimes rather than try to remember a new rule. So we're going to do the ln of 3x over the ln of 5. All right, remember ln 5 is just a number. So we're going to do y equals 1 over ln 5 times the ln of 3x. This is a constant, so when I take that derivative, I'm going to get dy dx equals 1 over ln of 5 times the derivative of ln of 3x. Remember, that's an old rule, so it's 1 over 3x times 3. And the 3's will cancel out. So we're going to literally get 1 over x times ln 5. And that's my dog singing, "You can do it." It's only the change of base formula. See? He's singing to you, "You can do it, you can do it." All right, he's so happy that this slide is over. That's the only example I think that you need. It's really just applying an old rule to something new and then taking the derivative in that form. All right, me and my dog are leaving now. Bye.